Hello everyone, in this video I'll be talking about Friedel-Crafts Alkylation, and briefly I'll talk about Friedel-Crafts Acylation, but I'll make another separate video where I'll be discussing in the next video about Friedel-Crafts Acylation in more detail, but here I'll be focusing more on Friedel-Crafts Alkylation. It's an organic chemistry name reaction and given by two scientists, Friedel and Crafts. And as from the name it indicates it's alkylation, so it's introducing the alkyl group. And as you are already familiar what is the alkyl group, it's addition of a methyl, ethyl, propyl, butyl chains across the benzene ring, that is called Friedel-Crafts Alkylation. So the starting materials for this reaction are benzene and alkyl halide and any Lewis acid, and this is the R group which you will call alkyl part. And the bonds that are formed in this reaction are carbon-carbon bond formations. So we can categorize the Friedel-Crafts Alkylation reaction as a carbon-carbon bond forming reaction. And the bonds that are being broken are CH bonds. And bonds that is, these are the side products. We wouldn't be focusing. So in short, we say that we can add methyl, ethyl, propyl groups across benzene using Friedel-Crafts Alkylation, and in order to do that we would require benzene, number 2 alkyl halide, and number 3 Lewis acid, and if we mix these three things together then we will get the alkylated benzene. So there are some situations that Rx means alkyl halide must be an alkyl halide, typically alkyl chlorides, bromides or iodides. So X should be any halogen atom. Moreover, Lewis acid often aluminum chloride but can vary widely ferric chloride or zirconium chloride. So this is the Lewis acid AlCl3 which is commonly used in Friedel-Crafts Alkylation. For example, if you have these alkynyl halides such as this one having a sp2 carbon there and halogen next to that, this will not work for Friedel-Crafts Alkylation because of the electron richness of the double bond. This halogen is not a good leaving group in that condition, so we cannot use the unsaturated alkyl halides, I would say. Moreover, we also cannot use the alkynyl halides. What I mean by alkynyl halides is any halides directly linked with the triple bond. We cannot use them as electrophiles in the Friedel-Crafts Alkylation. As you know that in organic chemistry, whenever a reaction takes place, then there is an electrophile. That's what we call E, and it is denoted with positive charge mostly. And second part in organic reaction to happen is nucleophile. We write Nu and we put negative charge. So the reaction, any organic reaction takes place between electrophile and nucleophile. So nucleophile is something which is rich in electron, and electrophile is something which is deficient electron, having electron deficiency. So in the Friedel-Crafts Alkylation, this Rx part is called electrophilic center or electrophile, and this benzene is called the nucleophile. So the nucleophilic character comes from the benzene and the electrophilic character comes from the alkyl halide. And Lewis acid, aluminum chloride, acts as a catalyst. So this is the introduction of Friedel-Crafts Alkylation. So I will be briefly describing Friedel-Crafts Acylation here in this video, but in my next video I'll be discussing in more detail about Friedel-Crafts Acylation. So generic example of Friedel-Crafts Acylation is, again, we would start with the benzene that will act as a nucleophile, this one. Now instead of alkyl halide we would require the acid chloride and acyl group to transfer the acylation. That's what we call acylation. So the difference between alkylation and acylation is that in alkylation we introduce only R group, but in acylation we also add R group, but also we add the acyl part. So this group is called acyl group, where R is connected with the carbonyl group, and X is usually a halogen. This X is usually a halogen which acts as a leaving group. It could be chlorine, bromine, iodine, although anhydrides can also be used instead of acid chlorides. So now in this Friedel-Crafts acylation, benzene is acting as a nucleophile, and acyl group or acid chloride is acting as an electrophile, and again this is also Lewis acid catalyzed reaction. So there are few things common in between Friedel-Crafts alkylation and Friedel-Crafts acylation. So they both, alkylation and acylation, require benzene to act as a nucleophile, and they both need Lewis acid to catalyze the reaction. The only point of difference between alkylation and acylation is from their names is also indicated. So addition of acyl group is called acylation, and addition of alkyl group is called alkylation. That's the main difference. And also there's one more common thing between alkylation and acylation, that Friedel-Crafts acylation is also carbon-carbon bond formation reaction. We can categorize or we can classify Friedel-Crafts alkylation as well as Friedel-Crafts acylation, both reaction as carbon-carbon bond forming reactions. The bonds that are being broken in both the reactions are same, that is the CH bond broken in alkylation and CH bond is broken in the acylation as well. So the products are different. That is the major difference between these two reactions. In the Friedel-Crafts reaction we get alkylated benzenes, but in Friedel-Crafts acylations we introduce a new functional group directly attached with the benzene ring, that is called ketones. So we can prepare aromatic ketones or aryl ketones. So this is aryl ketone. So aryl ketones can be synthesized from the Friedel-Crafts acylation, and this is also method of preparation for ketones. So this was the basic difference and basic similarities and differences between Friedel-Crafts alkylation and acylation. And now let's move on further to discuss in more detail Friedel-Crafts alkylation in this video. But if you are really interested to find out about Friedel-Crafts acylation, then I'll be making another video about acylation next. Then you can watch about acylation. But here in this video, I'll be limiting myself to Friedel-Crafts alkylation, and we'll be discussing the mechanism of Friedel-Crafts alkylation, the limitations of Friedel-Crafts alkylation as well. So Friedel-Crafts alkylation of aromatic rings, when an alkyl halide is treated with a Lewis acid in the presence of an aromatic ring, it could be benzene or any other aromatic ring, the alkyl group can be added to the ring, forming CC bond with the loss of a CH bond. This electrophilic aromatic substitution, the name of reaction will be electrophilic aromatic substitution. The reaction is known as Friedel-Crafts alkylation reaction. Generally, no reaction occurs in the absence of Lewis acid. A common choice for the Lewis acid is aluminum trichloride, that is the commonly used Lewis acid, but many others may be used such as FeCl3 among others. Moreover, alkyl halides, typically chlorides, bromides, and iodides must be used, as the reaction fails completely for alkynyl and alkynyl halides. So we cannot use alkynyl or alkynyl halides for Friedel-Crafts alkylation. So it must be the alkyl halide must be based upon the simple saturated alkyl halides. Okay, let's move on to the next. This is the reaction that we discussed, what is Friedel-Crafts alkylation, and the reaction takes place between benzene and alkyl halide in the presence of Lewis acid to give you this alkylated benzene. And the R must be alkyl halide, and halide could be chloride, bromide, iodide, and the Lewis acid most commonly used is AlCl3, but however we can also use TiCl4 and zirconium chloride. Here's a specific example using the ethyl chloride. So if you want to introduce or if you want to prepare ethyl benzene from benzene, starting from benzene, then you can react benzene A with ethyl chloride. That will be B, and that will give you the C, and the bond formation reaction is CC. The role of the Lewis acid in Friedel-Crafts alkylation is to activate alkyl halide. That is the common question that people ask in the Friedel-Crafts alkylation, that why we are using the Lewis acid in Friedel-Crafts reaction. The simple answer, the short answer is to activate the alkyl halide. So if no reaction occurs in the absence of the absence of a Lewis acid, then what is the role of the Lewis acid here? Like we saw in the two previous posts on electrophilic aromatic substitution reactions, Lewis acid activates the electrophile by according to the leaving group, making it a weaker base and a better leaving group. Better leaving group is a weaker base than chloride. So the end result is that coordination of Lewis acid to the electrophile makes the species a better electrophile. So we can summarize that why we are adding the Lewis acid because of the presence of this thing, okay? And the purpose of adding Lewis acid is to make the electrophile better by making a better leaving group. With secondary and tertiary halides, full dissociation to a carbocation can occur. In the case of primary and methyl alkyl halides, the electrophile is likely not a free carbocation but a carbocation-like species, where the CCl bond is considerably weakened or lengthened. As we mentioned briefly, no reaction occurs with alkynyl or alkynyl halides, largely because of the carbocations of these species are so unstable and difficult to generate. That is the reason why we cannot use alkynyl or alkynyl halides or halides based upon sp2 or sp3 alkyl halides. So as we mentioned briefly, no reaction occurs with alkynyl and halides. So let's look further how and what is the mechanism of Friedel-Crafts alkylation. So the step 1 in the mechanism of Friedel-Crafts alkylation is activation of electrophile with Lewis acid. In the case of secondary or tertiary alkyl halides, full dissociation to a carbocation likely occurs. For example, this is the alkyl halide. So first, the free lone pairs of chlorine attack on the electron deficient atom, that is aluminum, which is Lewis acid. The bond making takes place between chlorine and aluminum, and chloride as a result gets a positive charge, and aluminum receives the electron and hence gets the negative charge. The bond between this carbon and this chlorine is weakened. So the bond between CCl bond is weakened, and as a result the bond dissociates, or bond is being broken between carbon and chlorine, and we generate this carbocation as an intermediate. That is the purpose of the Lewis acid. So Lewis acid activates the electrophile, makes it a good leaving group. And now AlCl4 negative is a better leaving group than Cl negative. For primary and methyl alkyl halides, it is unlikely that a free carbocation is present. So This sort of a transition state is observed when we have primary or methyl alkyl halides. So instead of a full carbocation generation, in this case of secondary alkyl halide, this is a secondary carbocation. But in case of a methyl or alkyl, we just get a partial positive and partial negative charges, and the weakening of the bond between carbon chlorine takes place in that case. The key CC bond forming step is to attack of the aromatic ring upon the carbocation or carbocation like electrophile. That is a key step. Once the electrophile has been activated, the next step of the Friedel-Crafts is to attack of the activated electrophile by the aromatic ring. This is also the rate determining step, as it disrupts the aromaticity of the ring, and it's approximately 36 kilocalorie per mole of the resonance energy. In this step, a CC pi bond from the aromatic ring breaks and a new CC sigma bond is formed, leading to a carbocation intermediate. Now if you look at this one, this is the benzene, which acts as a nucleophile. Now this is electron rich species. You can attack benzene pi electronic cloud can attack on the carbocation to give you this pi intermediate, sigma pi intermediate. So it's an electrophilic aromatic substitution, and this is the rate determining step, make sure, and the CC bond formation takes place, and in the last step the re-aromatization of this benzene takes place. This is the last step, step 3, deprotonation at carbon to regenerate aromatic ring. So this aluminum tetrachloride now picks this proton, and this positive charge is vanishes, and we generate the benzene having the alkyl group. So this is how we can introduce the alkyl group on benzene ring using the Friedel-Crafts Alkylation. This is the mechanism. If you haven't understood any, you can re-watch the video, or you can post the comments below in this video. Now there are more things to look out in the Friedel-Crafts Alkylation. Look out, carbocation rearrangements can occur in the Friedel-Crafts Alkylation reaction. Many university science courses are taught in units where what you learn in one module has pretty much zero overlap with what you learn in another. Needless to say, organic chemistry is not like this. You have probably already experienced a situation where concepts you learned in Organic 1 revert back to Organic 2 chapters in unexpected ways. Well, get ready for another fun example. We showed above how ethyl chloride reacts with benzene and AlCl3 in the Friedel-Crafts Alkylation to provide ethyl benzene. Extension of this reaction from ethyl chloride to propyl chloride should correspondingly give propyl benzene, right? Now let's look at that, and that will be a rearrangement. Now we should expect that propyl benzene should form when benzene reacts with the propyl chloride in the presence of Lewis acid, that is aluminum trichloride, but this product is not formed. This is formed. This is the rearranged product. Strange things afoot in the Friedel-Crafts Alkylation reaction. The Friedel-Crafts Alkylation reaction between propyl chloride and benzene does not give propyl benzene but isopropyl benzene. What happened here? What the isopropyl benzene? Okay, how did this formed? How did this happen? Let's have a look at this. This is the primary carbocation, less stable, so we observe there's an observation of a 1,2 hydride shift. So what happens when you have a carbocation formation? Then sometimes it is stabilized either through 1,2 alkyl shift, or it is stabilized through 1,2 hydride shift. So in this case, primary carbocation stabilizes itself by 1,2 hydride shift, and now this is secondary carbocation, which is more stable than the primary carbocation. But if you are not familiar what is carbocation and what is the stability and everything about carbocation, then I have made several videos about carbocation chemistry, then please watch them to familiarize yourself with the carbocations. The hydride shift. Carbocations can rearrange via hydride and alkyl shifts such that a less stable carbocation is transformed into a more stable carbocation. That is the reason why we observe why there is a 1,2 hydride shift or why there is 1,2 alkyl shift. That is the reason. In the Friedel-Crafts, we have seen that coordination of a Lewis acid to an alkyl halide resulted in a carbocation. or in the case of primary alkyl halides, at least a carbocation-like species that is then attacked by the aromatic ring in the rate determining step are observed. Now if you look at this one, if a hydride shift or alkyl shift will result in a more stable carbocation, it will happen. So what is happening here is really not different, or no different. If a carbocation rearranged to a more stable carbocation through a hydride alkyl shift, it will do so. And if you look at here, in the Friedel-Crafts Alkylation reaction, carbocation rearrangements can occur. For example, this is the carbocation which is stabilized through 1,2 hydride shift to give you the secondary carbocation. And the rearranged carbocation is the electrophile in electrophilic aromatic substitution. Now if you can see, this is isopropyl benzene instead of the propyl benzene. Bottom line for the Friedel-Crafts alkylation is this. Assume the alkyl halide goes through a carbocation. Assume that if the carbocation rearranged to form a stable carbocation through a hydride alkyl shift, it will. Okay. Limitations of Friedel-Crafts alkylation. First, as we have seen, carbocation rearrangements can occur. There are ways of circumventing this issue indirectly, which will hint below. Second, Friedel-Crafts alkylation tends not to work well with the electron-poor aromatic rings, particularly strongly deactivating substituents such as CF3, nitro, sulfonic, and so forth. Halogens are okay. Number 3, third limitation is this is a more of a practical issue than anything else, so is often ignored. The product of the Friedel-Crafts alkylation is often a better nucleophile than the starting material. Recall that alkyl groups are activating. The result can be a bit like the cookie monster in a Chips Ahoy factory. It can stop at just one, resulting multiple alkylations. These are the 3 limitations of Friedel-Crafts. So one should avoid Friedel-Crafts reaction, and instead of using it, use the Friedel-Crafts acylation. I hope you learned about Friedel-Crafts alkylation in detail with mechanism and limitations and all the details. But still, if anything is missing, then feel free to comment below and I'll get back to you. But in next video that I'll be talking about how we can overcome the limitation of Friedel-Crafts alkylation. Take care, thanks for watching, and see you with the next video.